Okay, next up, now that we know how to find volume, I want to just take one day here and go back and talk about similar figures. All right, when two figures are similar, because you'll notice there is a pattern. If two figures are similar, there's a pattern between their one, perimeters, two, their areas, and three, their volumes. So that's what we're going to look at today. Two figures are similar. What's so special about one, their perimeters, two, their areas, and three, their volumes? I just want to go back to what do we know about two similar figures? I have two similar triangles up there by angle. If the two triangles are similar, we know number one, corresponding angles are congruent. What about the sides? They are not congruent, but they are in the same ratio. And we've been using this term a lot, and let's go back to it. That ratio that the sides are in is called the similarity ratio. So can you find the similarity ratio right now for me between those two similar triangles? Match up the congruent angles and let me know two sides that match up. Okay, find the similarity ratio between these two. Again, it's the ratio of two corresponding sides up here. And I'll take any version. I will take any version up here. Any version. Zach, when you're ready, the similarity ratio.
What? Okay. I'm opening my packet.
Gotta crawl before you walk, kids, right? All right, we'll get back to you there. We got to move on here. Abby? Okay, 12 to 8 would be, I'm just going to go left to right. 8 to 12, fine. You could also reduce it. 2 to 3 would have been fine. If anybody was going to give me 10 over 15, if anybody was going to give me 14 over 21, all would have been fine. Yes?
Technically, could you have also said 1 to 1 1/3?
Sure, but I'm not getting that crazy there, Connor, so relax. Okay? All good here. Finding the similarity ratio. Okay, because that's going to be important coming down the road here. All right, let's go. Two similar rectangles up here. Two similar rectangles. First question right off the bat, can you guys find me the similarity ratio, please? Find the similarity ratio between 1 to 2. And everyone now, Abby did give me her order, and I said, let's go left to right. Notice it does say a specific order here. Rectangle 1, 2, rectangle 2. So please give it to me in the correct order here. So what's your similarity ratio between these two here? Let's start it off. Aditya, what do you have?
1.5.
Okay, I need a fraction though. This to this.
2/3.
2/3, yes, 2/3. Again, if you got anybody kept it 10 to 15 or 16 to 24, I'm good. I'm a reducer though, so I like to reduce. Next up, can somebody find the perimeter of rectangle 1 for me? Perimeter of rectangle 1. Should go pretty quick there. Perimeter of rectangle 1. And we'll find out some breaking news here. When you're ready there, Henry, perimeter of rectangle 1. 52. Yep. Everyone did 20 plus 32. The opposite side's congruent for a perimeter of 52. And please do the same thing for rectangle 2, everybody. What's the perimeter of rectangle 2 up there? Henry, once again, perimeter master. 78. We did 30 plus 48. We get 78. And now here's where the magic happens. Ready to go? What's the ratio of their perimeters from 1 to 2? The ratio of their perimeters now. Here's where the magic happens. And the ratios, when you're ready there for me, Violet. Excuse me, what is it? 2 to 3. Look at that, kids, huh? 2 to 3. So what did we just learn here? Whatever the ratio of the sides are, that's the same as their perimeter ratio. So theorem number 1 today. S1 over S2. What do you think that's going to represent? Okay, I don't. Here's the thing. You are correct when you say side. I don't like to say sides because if we're like dealing with a cylinder, cylinders don't have sides, right? So we're just going to say that's the similarity ratio. All right, and let me explain here. Similarity ratio. S1 over S2 is your similarity ratio. It's anything that corresponds to each other. Like I just mentioned cylinders, you could say the radii. Compare the radii, and that's the similarity ratio. All right, it's whatever corresponds to each other. And what did we just learn? That's the same ratio. What's going to be in? The perimeter, P1 over P2. Always the same ratio. And again, P1 over P2 is the perimeter ratio. Always the same. All right. Whatever the similarity ratio is, the perimeters will be in the same ratio. Questions on the perimeter. Does that hold true for area ratios? Does the similarity ratio and the area ratio, will they always be the same? Let's check it out. Since we're in the area unit. I won't ask anybody this question. It's the same same two rectangles. So my similarity ratio from rectangle 1 to 2 is 2 to 3. All right, real quick, what's the area of rectangle 1? We just quizzed on this last week here. Not too bad. Kevin, area? 160. We do length times width, 10 times 16. So we do get 160. Yep. And then everyone go ahead, find the area of rectangle 2. When you have that, let us know. Rectangle 2's area there. Jacob? 360. 15 times 24. Good, everybody. And here comes the magic now. What's the ratio? Don't assume it's 2/3 either. You better check on your calculator. What's the area of the ratio for 1 to 2? Shoom. Theo? I'd like it reduced, please. I know it's 160 over 360, but.
I got 4 over 9.
Yes, you did. All right, so we can at least say, are they equal? No, they're not, but they do have a relationship. If you knew the similarity ratio, here's what I do to it to get to the area ratio. So let's start by writing something incorrect in the theorem, and then you can fix it for me. So let's say we know the similarity ratio, S1 over S2. We have clearly shown that that is not the same as the area ratio. Because 1 was 2/3, the area ratio was 4/9. They're not equal. Just make sure we know before we move on that this is the area ratio. Can somebody adjust it? What do I have to do to that similarity ratio to get to the area ratio? 2/3 to 4/9. We probably should do another example. Don't have the time. Kira, what do I need to do?
You have to square the similarity.
I have to square the similarity ratio to figure out what the area ratio is. Oh, whoa. Oh, wait a second. Wait. Kira, what do I have to do again?
You have to square the
Square it, and we're talking about area? Oh, yeah, that makes sense, because if we did write units, what do I always tell you? Units have to be what for an area problem? Squared. Okay? It's got to be squared. All right, so the similarity ratio, we got to square it to get the area ratio. And now that we've done all this, I think you can probably predict what's going to happen as we go to volume. All right, I couldn't keep a rectangle because rectangles don't have volume, so I changed it into a cube. What's the similarity ratio from cube 1 to cube 2? Shocker, it's going to Abby. 2/3 remain the same. And what's the volume of cube number 1? Base, area of the base times the height. Choom. Connor, when you have that?
For cube 1?
Yep.
8.
8. 2 times 2 times 2. And how about cube 2 when you have that? The volume of cube 2. Take your time when you have it. Thanks, Kira. Hey, that's all you need to do because I would have taken another 2 minutes to figure out it was you. 27. What's the ratio of cube 1 to cube 2? Don't get freaked out. Don't get freaked out when you punch it into your calculator. Just let me know here. Melissa? Yeah, it doesn't reduce, so it's 8 over 27. Obviously not equal to the similarity ratio. All right, obviously not equal, but let's fix it. If I know S1 over S2, this is clearly incorrect based on our work above that it's not equal to the volume ratio. Fix it, right? Fix it. Zach,
You cube it.
cube what?
You cube the similarity ratio.
Cube the similarity ratio. Shocker, because how do I leave my units in any volume problem? Cubic units, yes. So all of you are noticing if you know the similarity ratio, you have some power to find the perimeter, area, and volume ratios. Now the question is, how do I apply these three theorems right now? How do I apply these three theorems? All right, let's do it. All right, so one side of a hexagon is 6. The correspond. What am I giving you right there? One side of the hexagon is 6. Corresponding side is 9. What am I giving you right there? That's my what? That's my similarity ratio right there. That's S1 over S2. I'm telling you one area of the smaller one's 48 square feet. What's the area of the larger one? All right, and I don't want to draw a hexagon out, put a 9-foot side, and then try to figure out. By the way, I can't do that. If anybody's going to start pulling this on me, oh, okay, all right, I remember doing this. Where's my hexagon? There it is. Hexagon, and then you start doing this on me. Similar hexagon, 9 side. I can find that, right? Do this. Find that. No, because they didn't tell you this hexagon was regular. So not all those triangles are congruent. So everyone see, I can't do, 1/2 base times height times 6 anymore. All right, all these triangles will be different because it's not a regular hexagon. But, can anybody tell me what ratio my areas will at least be in? I know the similarity ratio is 6 over 9. Can you figure out what the area ratio will be? Yeah, what do I need to do to the 6 and the 9 to find the area ratio? There's the similarity ratio. Aditya, what do I need to find the area ratio? What did we just write down a couple minutes ago? What do I need to do to the similarity to get to the area? Square it. Everyone right? So instead of using 6 over 9, I'm going to use 36 over 81. I know these hexagons are in a ratio of 36 over 81. That's not saying one area is 36 and the other is 81. What I'm saying is whatever the areas are, that's the ratio. What area do I know? The smaller or the bigger one? Smaller or bigger area? Which one do I know there? Going. Take it, Tiffany. Which one do I know? The smaller one. So we'll go with the smaller ratio number in the ratio 36. And now you could solve for the area of the larger one. All right, the ratio of the areas is 36 to 81. Smaller one's 48, so what's going to be the area of the larger one? But you cannot use 6 over 9 in the ratio. I need to square it first. So go ahead, do your cross multiplication. And what is the area, Connor, of the larger one?
I'm still working.
Okay, when you have it, let me know.
108.
108. Yep, square feet. If you know the ratio, what the ratios are in, the volume, perimeter, or in this case, area, you can find the other one. Questions on number 1? All right, I know there's some people feeling uncomfortable, which is fine. That's why we got a couple more. All right, these two I don't know what they are, quadrilaterals. They're similar to each other. Notice I'm giving you the area of both, but I want one of the corresponding sides now. I want one of the corresponding sides. All right, so let's see. Watch what I'm going to... X. What did I just set up there? What ratio is that? That's my slash similarity ratio, right? Everyone, x over 14, that's my similarity ratio. Now, if I do this, correct or incorrect? Why is it incorrect? You're saying that S1 over S2 is equal to the areas. That is false. We proved already, what do I need to do to the similarity ratio to get to the area ratio there? Melissa, what do I need to do to that similarity ratio? Square it. And now I have a proportion I can solve. If anybody, was anybody thinking take the square root of 27 and 147 and setting it equal to x over 14, you could do that too. All right, but I'm just going by what I showed in the theorems here. Take your time. This should be a whole number. That's why there's no rounding directions. And there should be no factoring here either. All right, what do we got here? Theo, when you're ready.
6.
Yes. Great job. Theo, what elementary school do you go to? You're going like that? All right. Usually I ask some follow-up questions, but if you didn't go to Slingerlands, I don't care. Okay. Who'd you have for 5th grade? It was that impactful on you. 3rd, 4th grade, anybody you can throw out at me?
3rd grade, I had to spend it.
Okay. How'd that go?
Good.
All right. Good. All right. Anyway, moving on. Next up, questions. All right, a little bit different now with 3. Little bit different. I got a small cylinder of tuna. Anybody big tuna people? Tuna mayonnaise on the sandwich? No? Tuna sandwich? No, you don't. Nobody puts mayonnaise with it? Yeah, that's what you usually do, right? If you're a human being, yeah. That's what you usually do. The only thing I despise about it is opening it.
You don't like opening a can?
No. I like the little flip on the top and just pull it back. I hate using can openers.
Why?
I don't know. It's just sometimes it doesn't go well for me, and then you got all these punch holes in there. And then you start getting a knife and wrenching that thing up. Yeah. So sometimes, well, you start turning you punch hole it, and you start turning that bad boy, and sometimes it doesn't get deep enough, and then it's like, oh, I got a little sliver here, then it missed, and then I got a little punch hole in another sliver here, and started to open. Sometimes it doesn't open up well, and that fires me up. All right, anyway, got a radius of 4 centimeters and a height of 3.8. And then we got the large can of tuna. And it's similar too, good for us, it's similar. That's got a radius of 5.2 centimeters. What is the height? What is the height? Or sorry, what is the volume of the larger one? Excuse me, I don't need the height. What's the volume of the larger one? All right, what's given to me? Is the similarity ratio given to me? Do I have 2 corresponding parts up here?
Yeah.
Yes, and this is why I stress I do not like to say sides when I say similarity, S1 over S2. It could be any corresponding parts, in this case, the radii. So we know at least it's 4 over 5.2. That's my similarity ratio for the 2 cans of tuna. What I'm looking for is what's the volume of that. Well, let's start here. If we're talking volume, I can't use 4 over 5.2. What do I need to do to those numbers? Okay, I do need to cube them if we're talking volume now. But usually in these two pass problems, I would set up a given volume over X, the other one I'm looking for. But I did not provide that. Can you find a volume? I sure hope so. We're in the unit now. You can find the volume of the small tuna can. Pi r squared times height, or big B times H on your formula sheet. I'm getting about 191 with a couple zeros after. Everyone, 191. All right, plug it in now. Make sure it's for the. Make sure it goes with or across from the 4 cubed because it's the smaller can. Now we're solving for the volume. And then I want to talk about if anybody was thinking an alternative way to approach this, because there is. When you have it, take your time. Nearest tenth, the volume of this larger one. Take your time, Abby, whenever you're ready. Great work, great work. What? Your volume times 5.2 cubed, and then divided by, that would be 64, 4 cubed. Good job. Good job. Was anybody thinking alternatively to set up this? Ready? Here you go. Alternatively, you could have done 4 over 5.2 equals 3.8, solving for the height of the big one, and then using the volume formula on the big one. That's also another way around this one. Yes. Okay. That's also another way around it. All right. Ready for one more here to finish it up. Triangle KLM is dilated by a scale factor of 3. Nice. So is this KLM? Is this bad boy getting bigger or smaller? Bigger or smaller? Bigger. Scale factor is bigger than 1. And we're getting triangle DRS. Which statement is not always true? Whoa. You guys are going to have to prove some stuff to me. We didn't say those triangles are similar, but why are they similar? What did we just do to them? Dilate them. Angles change when you dilate? No, they do not. Angles do not change, so they remain similar when you dilate. So let's go through the choices. Is angle K congruent to angle D? Yes, because, again, similar triangles, dilations preserve angle measure. So that is a true statement. We're looking for the not true one. Remember, we dilated by a scale factor of 3. Is KM, side KM, a third of DS?
Oh, yes.
A third of DS. Yes, it is, right? It is. Don't get screwed up by that 3. It is a third. Is the area of DRS 3 times that of KLM? No. Ooh, no. Well, the scale factor was 3. The perimeters would be 3 times each other. But the area, well, remember, what do we have to do with area? Cube it. Or cube it? Square it, right? So this should have said 9 times. All right? That should have been 9 times the area. And then, whoa. Is the perimeter 3 times? Because they're always equal to each other, right? Sides are always equal. All right, play your cards right. We could get out of here with nothing, even though there's 11 minutes left.